Fractals in nature. Have you ever noticed that the size of a photo changes, but the shape stays the same when you zoom in on it? How would mathematics describe this kind of situation? If a figure is enlarged or reduced by a constant ratio, its size changes, but its shape remains the same. In this case, the two figures are said to be similar. Figures that match in this way are called similar figures. So, how can we tell whether two figures are similar? When we compare the lengths of corresponding sides, we find that they have a constant ratio. This ratio is called the ratio of similarity. Congruent figures can be seen as a special case where the ratio of similarity is 1:1. However, there is an important point that can be confusing. It is easy to think that the ratio of similarity also applies directly to area, volume, and angles. But this is not the case. Angles remain the same, but area and volume change differently. Area depends on length multiplied by length, and volume depends on length multiplied 3 times. So if the ratio of similarity is 1:2, the area becomes 1:4, and the volume becomes 1:8. The meaning of similar in everyday language is different from its meaning in mathematics. We often say things are similar if they simply look alike. However, in mathematics, figures are considered similar only if they have exactly the same shape when scaled up or down. Does this type of structure appear in nature as well? In fact, similar forms are easy to find in nature. For example, the leaves of a ginkgo tree vary in size but have very similar shapes. If one leaf is enlarged or another is reduced, they can closely match. But nature goes even further. Beyond simple similarity, it shows a much more remarkable repeating pattern called fractals. Fractals are patterns in which large and small forms repeat the same shape. Even when we zoom in, similar forms continue to appear. This property is called self-similarity. Fractals show that nature is not random, but follows underlying rules. Simple rules repeat to create complex forms, and these structures also help use space efficiently. It is easy to understand this concept by thinking about a tree. Branches grow out from the trunk, and smaller branches split off again and again. As this process repeats, the overall shape of the tree takes form. If we zoom in on part of a branch, we can see a structure similar to the whole tree. A similar pattern appears in the veins of leaves as well. These structures help trees transport water and nutrients and absorb sunlight efficiently. Lightning shows a similar structure. Instead of falling in a straight line, lightning spreads out and branches in many directions. Even the smaller branches resemble the overall shape. This structure forms as electrical energy searches for the most efficient path. Depending on air conditions, temperature, and voltage, different fractal forms can appear. Romanesco broccoli is another striking example. Small, cone-shaped clusters repeat to form the whole, arranged in a spiral. If we take a small piece and look closely, the same structure appears again. Fractal theory began with the study of coastlines. The length of a coastline changes depending on how it is measured. The more closely it is measured, the more detail appears, and the longer it becomes. This is because small parts repeat the same complex structure as the whole. This feature is also seen in clouds, mountains, and the flow of rivers. Why does nature create such structures? Scientists believe the answer lies in efficiency. By following a simple rule and repeating it, nature can grow and move while using the least amount of energy. Although these structures look complex, they are built on simple principles. In the end, the complex patterns we see in nature come from the repetition of simple rules, and the study of fractals begins from this idea.